My name is Andy Newsome, and I'm the Director of the National Schools Observatory. And this is an introduction to how you can use the Liverpool Telescope through the National Schools Observatory to help with your GCSE astronomy observations. So we're going to be covering why robotic telescopes like the Liverpool Telescope are useful, how that fits into the observational tasks and how the NSO can help you, and then look at some of the details of how to get the observations, creating student accounts, the various different projects we think are suitable within the GCSE, and a little bit about how to make an image, and finally some suggestions for how your students can reflect on their observing. The first question is how you would use a robotic telescope from a school. Well, the idea is that you use it as similarly as possible to what professionals do. The way we work is we decide what we want the telescope to do, and we send a request to the telescope through the internet. That goes into a large system which schedules the telescope, and a night or 2 nights or 3 nights later, the observation is done for us and we download it. And so you and your students will be going through the same process, deciding what they want to observe, the details of the observation, the filter, the exposure time, the object to observe, and so on. That will get sent out to the telescope, along with all of the requests from professional astronomers, and then the telescope will do their observations at the best possible time. So they're not controlling the telescope live, they're not taking over control of the telescope, but they're working alongside professional astronomers. The reason why robotic telescopes are good for your students is that they can do it in their own time. You're not restricted to bringing in the students after school or even doing it during a lesson, or any of the sort of constraints which normally affect practical observing in schools. Also, the weather is much less of a problem, partly because the telescope doesn't have to be in the UK where the weather is dreadful. This particular telescope is in the Canary Islands, more than 2,000 metres up a mountain. But it's also because if there is a little bit of bad weather, the telescope will do your observation a little bit later. So it's very flexible. And the other advantage of the school's observatory is that it's free, so you don't have to pay for any of this stuff. You and your students can just come along and use it. So there are lots of advantages to using robotic telescopes. But there are also issues that you need to consider. The planning process is different. It's different from if you were actually getting a telescope out in your own school and making the observations yourself. It's not worse or better, but it is different. And there are some aspects you have less control over, because the telescope and the computer systems at the telescope are making a lot of the decisions for you. That means it's harder to get it wrong, of course, but it also means that the skills that your students learn will be slightly different. So you have to bear that in mind, and you'll have to look for aspects that your students can emphasize during their reflection. Our approach has 3 key factors that we decided were important. First of all, unlike the rest of the school's observatory, we want students to be able to get it wrong. They have to be able to make some kind of mistake because you learn from those. So that was a key factor in the way we set things up. And it's also important that the students can experiment. If they just come along, take one set of observations and that's it, they probably won't learn very much. But if they can try lots of different setups, different filters, different exposure times, different objects and so on, then they can learn from that, and again that gives them something to reflect on. And the final thing is it must be possible for the students to do the whole process entirely on their own. That doesn't mean you can't support and help them, but it should be possible for them to do it without any support or help. So they are the factors that have led to the system that we have set up. Your first stage is creating accounts for the students. Excel and Pearson's like each student to work with their own password-protected username. Now, we don't have students signing up directly because you need to be able to see what they're doing, so you're responsible for setting up accounts for your students. From your NSO teacher account, you can create any number of student accounts, there's no limit on this. So each of your students can have their own account with their own password. And with that, they can make as many requests as they like. Obviously, if they make thousands of requests, most of them won't get done, but there's no limit that we impose on the number of requests that they put in, and we will take as many of them as we possibly can. Once your students have their accounts, you then have to decide which of the tasks that Edexcel have set up are relevant. This is obviously the aided observations. The unaided observations are not appropriate for robotic telescopes. And having looked through the possibilities, we decided that there were 2 that were particularly suitable for robotic telescopes. So there's B1, looking at lunar features, and B11, drawings of Messier objects. So obviously they won't be doing drawings. They'll be taking images and processing them in a computer, but that fits into the same category. So they're the 2 that we have set up on the school's observatory website. It would be possible to do some of the other tasks, but they're not as straightforward and they're not as suitable for robotic telescopes. Starting with B1, I'll guide you through the process on the website in a few minutes, but first I'll just show you the kind of things that you can get. The idea behind B1, the lunar features, is that you're looking at changes as the lunar phase changes. So here's an example of an observation of part of the moon taken close to full moon. And you can see a couple of craters, and there's some nice rays where material has been thrown out of an impact crater, and so on. But if you wait a couple of weeks, and you take an observation of the same part of the moon at a very different phase, it looks radically different. In this case, the rays have disappeared, but there are many more craters, and so that's the kind of feature you're looking for. Now, we can't observe the entire moon in one go with this telescope. It's a research telescope. It's focused on detail rather than large images. But if you choose a particular part of the moon, you can follow that night after night, week after week, even month after month, and see these changes. So that's what you want your students to do. You want them to choose their personal parts of the moon and really look at how the changes in the lunar phase affect that part. And that gives them a lot that they can discuss. They can discuss the visual changes. They can discuss what the features they're looking at are, why it's important to look at different times to see different features, and so on. Once the students have logged on to the NSO website, they can then go to the Go Observing section and scroll down to find the GCSE Astronomy section. And within there they'll have three choices: lunar features, observations of a nebula or a galaxy, or three-colour observation of a nebula or galaxy. We're going to start with the lunar features, and we'll come back to the nebula and galaxy observations later. The first thing they will get is a summary of the lunar features program, just to check that this is exactly what they're looking for. Most students will just go straight to continue at this point, but if they want to go back and choose the other option, then they can do. The first real decision they have to make is about the timing of the observations. Now, the way we look at these is a start time and a length to continue trying. That start time will default to now, which is perfectly reasonable, but if the students want to plan ahead a bit and schedule observations for a month or two's time, then that's fine. They just change the date here. The duration is slightly more challenging to get right. It's very tempting to choose the shortest time possible, a day for example, because they think that will increase the chance of the observations being done quickly. But it isn't actually how the system works. It will always be trying as hard as possible. All this option indicates is how long it will keep trying before it gives up. So this should always be the longest time that the students can possibly consider. If they've only got a month before a deadline, put in a month. If they've got longer, they should put in 3 months or even a year. That gives the telescope much more chance to get the observations for them. They might be done much more quickly than that, but it won't give up until that period is over. I'm going to go for a month because I've left it a little bit late, but they might have a little bit longer. The next stage is to choose which part of the moon to observe. The telescope looks at detail. The field of the view of the camera is not enough to see the whole moon in one go, so they need to choose somewhere with a particular feature. Could just click at random, but it's much more sensible if they've done some research and chosen a particular feature of interest, a crater or a landing site or something like that. I happen to know there's a very nice crater here, so I'm going to go for that part. And I then need to decide how many observations to actually take. Somewhere between 3 and 5 is the option we give. 3 is enough, but if they go for 4 or 5, that will give them more options to choose from later. I'm going to go for 4 to give me an extra observation to play with, but 3 will be plenty for most circumstances. The other aspect of the timing is how far apart those observations should be. There's a shortest and a longest time here. The shortest time is how soon after one observation to try and get the next one, and the longest is how long to keep trying to get that observation before the telescope again just basically gives up. There's a lot of flexibility here, anything from 15 minutes to 4 weeks. Generally speaking, the students need to think about what they're trying to see. If it's too short, they may not see a change in the feature they're looking at, and so an observation will have been effectively wasted. If it's too long, the phase might have changed too much and they won't see the intermediate phases. It'll be too abrupt. So they need to think a little bit about that. The defaults of 2 days and a week are probably sensible, but they may want to adjust them a little bit. I'm going to reduce the smallest to 1 day because I want to see relatively small changes. And that's all the decisions they need to make. We at the NSO have done the final bit of working out the filter combination and exposure time because that's actually really difficult. 2-meter telescope is not designed for looking at something as bright as the moon, so getting the right combination of filters and exposure times for the particular instrument took us quite a lot of work. We don't want your students to have to go through that, so that decision has been made. And you can see here the 4 observations are ready to go off to the telescope, together with a little colour bar on the right-hand side, showing when the observations could be taken. This is essentially when that part of the moon is illuminated during the night. So in this particular case, it will try immediately, but there'll be a gap for a week or two in the middle of October where that part of the moon isn't illuminated, and so it can't be observed. And if the student is happy with all that, then they can scroll to the bottom and click on Submit Observations, and that will now be sent off to the telescope. You'll see they've been given their unique code. Mine is 15428A, and that will be sent out to the telescope in a few minutes, and it will immediately start observing as soon as it can. So basically, after sunset tonight, when the moon is risen. Students can see their own list of observations by selecting My Observations here. And as you can see, I've got 2 sets of lunar observations about to go out to the telescope, or they can go straight back to the Go Observing and try again. Maybe a different feature of the moon, or perhaps look at different timing constraints to give them a fallback options. That's entirely up to them. The other option that we set up is B11, looking at Messier objects or NGC objects. This is in some ways more challenging for the telescope to do because it has to deal with many more possible changes in observing conditions. But again, that does give your students quite a lot to think about and reflect on. There are a lot of objects you can observe here. This is an example of a star dying, a planetary nebula. This is what the Sun will look like in a few billion years' time. And here we've taken an observation through 3 different filters and combined those to get a colour image, a 3-colour image. That is one recommended way of doing this, but it is possible to get very useful results with a single filter, and we've set both of those options up. This shows another observation of exactly the same object but under different observing conditions. Here we have relatively poor conditions. In the previous observation, what we call the seeing was good, so the image was sharp and clear. Here it's a little fuzzier, the atmosphere was a bit more turbulent. And one of the things your students will have to decide is how important are those very sharp images to them. Because if they really want the very sharp images, they can constrain the telescope, so it only observes when the seeing is excellent. But that is rare, and so they might have to wait longer, or it might not be possible to do their observations at all. Whereas if they're a little bit more relaxed and they don't care too much if it's a bit fuzzy, then the observations will be done quicker. Maybe they want to try one of each, one where it's fuzzy and one where it isn't, and compare them. So there are again lots of options available here. While at first sight this may look very simple, choose an object and point a telescope at it, there are actually a number of decisions that they need to make. Within the Go Observing section again, scroll down until you find the GCS3 astronomy options, but now we're going to be looking at the observation of a nebula or galaxy. Students can do this with a single colour or with a 3-colour observation. We're going to look at the 3-colour observation, but it's a very similar process for both. Again, a quick summary of what we're about to go through, plus some links to information about filters and the software they might use to take their final data and turn them into images. But then we'll continue. As with the lunar observations, the next choice which needs to be made by the students is the timing of the observations. When to start and how long to keep trying for. Again, starting now is perfectly sensible, but if the students want to plan ahead and schedule an observation of a particular object in a month or 2 months' time, then that's absolutely fine. And as with the lunar observations, the choice of how long to continue observing depends on how much time they have left. Choosing a shorter time will not speed up the observations. It will just mean that if after, say, a week, the observations haven't been taken, the observations will simply give up. So again, the default is probably a sensible time to choose here. The next step is to choose an object. Now, there are many, many millions of galaxies and nebulae in the universe, and most of them are inappropriate to observe like this. They're too small, they're too far away, they're in the wrong part of the sky or something like that. So we've narrowed that very large list down to a few dozen which we think are appropriate to this particular telescope and instrument. But there are still quite a lot to choose from, and this is where the students have to start using their astronomical knowledge, the different kinds of objects, and also when during the year an object might be observable. You will see that by default the list is given ordered by right ascension, and so the students should be able to use that information to work out what time of year a particular object might be observable. They can also narrow the list down. If they just want to look at galaxies, then type the word galaxy, and it will limit it to everything that is a galaxy. They might want to know a little bit more about objects, in which case they can click on one of the little information symbols, but I happen to know that I want to observe Messier 74. It's one of my favourite galaxies, and it's the right time of year for me to observe it, so I'm just going to go straight for M74. The next choice they need to make is about exposure time and filter. And this is another balancing act for the students. Short exposure times are easier for the telescope to schedule, so we'll be able to take the observations quicker and have a higher chance of them being done. On the other hand, longer exposure times give you better quality data, better quality images, higher signal to noise. Different filters also have different effects. They're ordered here from bluer and ultraviolet through to red and infrared, and they need to choose 3 filters, one for the red colour, one for the green colour, and one for the blue colour. There's help information about all of this that they can look at, but generally speaking the defaults for the filters are quite sensible. Exposure times they'll need to think about a little bit more. I'm actually going to go for 90 seconds for each, but again, the students might want to think about the object they're observing and how urgent it is for them to get their observations. Finally, a major choice that they need to take is about their observing conditions. The telescope will always try to take the observations at the best possible time, but the conditions in the sky change. Sometimes the sky is very bright because the moon is up. Sometimes there's a lot of turbulence in the atmosphere which makes the image fuzzier. So the students need to decide again what their balance is. The wider the conditions that they choose, the quicker and easier it will be for the telescope to take the observations. So if they want to take it when the sky is bright, dark, or any seeing conditions, then it will take it very quickly. But the image could be quite poor, the sky could be quite bright, which reduces contrast, or it could be quite fuzzy. So if they really want a very good image, they might restrict it to just the very best seeing and only when the moon is down and the sky is dark. But then there's a good chance that the telescope will not be able to get suitable conditions in the time that it has to take these observations. So there's always a compromise to be struck. I'm actually going to go for dark sky conditions, but I'm going to let the image be a little bit fuzzy, though not very fuzzy, so average and good seeing. And that's it. Now that is ready to be sent out to the telescope. There's a summary here of all the decisions that I've made, the filters and exposure times and the sky brightness and seeing conditions for the red, green and blue observations. And as with the lunar observations, there's a summary on the right hand side of when the telescope might be able to take the observations. This particular one you'll notice is very good around the 10th of October and poorer around the 25th of October. And that's because I've chosen dark moon conditions, and that's the period of time when the moon is new and so it isn't up during the night. If I'm happy with all that, then I click on Submit, and as before, that gets sent out to the telescope. I have my code here, and I can go back and check in my list of observations, and you can see here that it's been submitted and will soon be sent to the telescope. So, hopefully everything's gone well. Your students have requested their observations, the requests have gone out to the telescope, the weather's been good, and they've got their observations back. The thing to do now, of course, is to turn those observations into images. Now, we don't provide pictures. What we do is provide observational data. The camera is a research camera, and what it measures is the amount of light coming from an object into each pixel. And so we provide what are called FITS files, which stands for Flexible Image Transport System. It's the standard format used by telescopes all over the world. To turn those FITS files into images requires special software. We provide a piece of software called LTImage, which is designed to be very simple and easy to use, but there are many other ones which you can choose from. On the NSO website you'll find software tutorials in the help section which will guide your students through the use of LTImage, but again, if you want to use something different, then obviously feel free. But one thing I want to stress here is that there's often no right or wrong way of doing the image processing. The camera is more sensitive than our eyes. It can detect more detail than our eyes can, and so when you put data into the software and start processing the image, you're making decisions about what you do and don't want to emphasize. So, for example, this is an image of a galaxy, NGC 6946, taken through a single filter. So it's a single black and white image, and it shows some of the features of the galaxy. You can see the core, you can see the faint spiral arms. But if we take exactly the same observation and simply impose a false color scheme on it, we get this. And suddenly, some of the features become a lot clearer, and that might be something that your students want to do. They might want to reflect on the use of false color to bring out details. This is with a single filter observation, but you can do even more if you have 3 color observations, which can be combined to produce an image like this. So leave time for the students to experiment with processing their images, practice with some of the images from the archive so that they can get some idea of what they can and can't do, and what they can and can't bring out of their data. So once they've got their images and they're happy with them and they've thought about what they want to bring out, the final stage is obviously the reflection. There are several things that we would suggest the students think about here. They can't talk in a lot of detail about how they set up a telescope, how they plan their observations on a particular night and so on, because that's not how robotic telescopes work. But there are other things that they can think about and reflect on. One of the most important is they should explain their decisions. Not just what they chose to do, but why they chose to do it. Why did they choose a particular exposure time? Why did they choose a particular sky brightness conditions, and so on? For this, comparing observations can be interesting. And they could consider measurements. The specification may not ask for measurements, but there's no reason why they can't do them. So they might want to measure the size of a galaxy, or the diameter of a lunar crater, or something like that. And this can, if they want, lead to further discussion. So the size of a galaxy, for example, tends to depend on how you process the image, because you see more or less of it. And that could be interesting from a scientific perspective. Do you have to be very careful what you mean by size, when it changes depending on your processing, and so on. So I hope that's given you an idea of how the NSO can help you with your observing. And just to round off, I put up what I think I would consider to be 4 top tips. And the first one is, there's often no right or wrong. It's very tempting for students to think that they're doing the right thing or the wrong thing, and if they get something different from another student, then one of them must be wrong, and it isn't like that. A lot of what we're asking the students to do when they're choosing their constraints for their observations or processing their image is decide what they want to emphasize. So they're making decisions which lead to a final result. And if those decisions do lead to that final result, and they see the features they're interested in, they explore the aspects they wanted to explore, then they are right. Even if another student has done something very different. The second top tip is experiment. Don't just ask your students to get one set of observations and leave it at that. Allow them to take several. Allow them to compare and contrast between their results, because they will learn more and they will have more to reflect on. And because of that, it's important to leave time to explore the image processing. This isn't just about getting the observation, it's about what you do with it afterwards. And so they will need to practice that, possibly with archive observations, possibly with their own first attempts. And the final thing this all leads to is start your students observing as early as possible. It seems at first glance to make sense to start the observations once they've done most of the course material, because they'll understand the objects they're looking at better. But actually there's another argument which just says get them observing right from the beginning. And even if they don't know exactly what they're looking at, it might encourage them to learn. So the earlier they start observing, the better chance they have of getting a really good set of observations. Hopefully that covers everything you need to know. There's obviously more information on the website itself, or you can contact us on social media, and I hope you and your students do very well in their GCSEs. Thank you.